Good morning, everyone. Uh, like I said, this is a flexible day. As I promised, all of the new tabs on Blackboard are available. The Test 1 tab, which is where you go to access the test. And then, of course, there's a test number 1 work, and that's where you go to upload your files. So again, this is actually going to be, fairly seamless. Like I say, after you complete your test, scan your work, and to create one file, and then go to the test work tab, test number 1, and you have the Turnitin app, and you will just upload your file. So again, what I wanted to do today is just basically recap some ideas that we've studied in preparation for this test. Some of the problems I will do were actually questions from some of my conference hours that I found to be really good problems. Students would say, "Oh, how do I do this?" Or I figured it out, but what is more insight or whatever. So I do that with all my classes. Lots of times the questions you ask turn out to be really good example problems for lecture. So just remember with the testing window, it's on today. I will have all of my regular office hours today, as I normally do. I will send the email invitations. And then, of course, I have an office hour on Friday in the morning. And so if you would like to spend some time in the conference hours preparing for the test, that's fine. And then move your testing day to Friday. You have until 11 p.m. tomorrow. So keep that in mind as you plan your schedule. Again, I give a larger window basically to give you the opportunity to set a schedule that works for you. And since we're in an online setting, I think certainly that's the most fair thing to do. And so as you prepare, I wish you well, and please continue to attend the conference hours, and I will answer your WebAssign messages and send you information outside of the WebAssign if I need to give you more detail. So let's go ahead and get started. And good morning to everyone. Everybody's always so kind. I wish I could clone some of you and put you in all my classes, but I know that's not possible, and I'm not Superman, so that's not going to happen. Now, like I say, I want to do some examples from old test and also some conference hour problems. Let me get my IPEVO set up. It's got a mind of its own, which is probably good. I think, like I say, I say this every time, it's the best purchase I made when the COVID hit. And then, of course, the second is the new computer. So I'm grateful for that. So let me close this and then reopen. Now it sees the IPEVO. There we go. Now, the first thing I wanted to do, ladies and gentlemen, is just to say some more about inverse functions. So look at it this way. You're thinking, oh, well, Professor Ron's just going to cover everything we've talked about. Well, things will be covered, but that doesn't necessarily mean that every concept we've described will be on the test. I mean, there's a limit as to how many problems you can put in. On your test, you have 20 questions, and they'll all count 5 points. And of course, your work must support your answer. I have in the directions, an unsupported answer is a wrong answer, and that I will abide by that. Your work must support your response. That's what we do in a math class. Remember, this is not a standardized test where fidget a little bit and guess, okay? If that's what you're doing, then that's not why we're in a math class. So as you work through the test, just say, okay, well, I know this, I know that, we talked about that, but I do put in lots of effort to make sure I get good coverage. But that doesn't mean every nuance that I've talked about will be covered. You just have to have a good foundational understanding. So for this first example, what I did was just to give you a function, and what I'm asking you to do is just maybe some basic ideas. Prove that this is one-to-one. Maybe that might be a question, or maybe on the test, I'll just say compute F inverse, and you would know that it would have to be one-to-one. And then maybe we'll go ahead and get the range and domain of F inverse, and then compute F inverse. So this is a nice, just standard problem. This will come throughout. And let me make one more comment. I get a lot of messages on WebAssign about inverses. And the question would be, well, Professor Rana, I think I did this right and it's computing correctly, but here's an issue that I'm seeing. Make sure that the formatting is correct. For instance, in calculus, when you add an arbitrary constant to an antiderivative, WebAssign says use an uppercase C. If you don't use an uppercase C, it kicks the problem out because it's scanning for that uppercase C. So when there's a variable that's presented in the problem, then you must use that variable. Or if there's a function notation and there's an input variable, then that input variable is what you need to use in your formula. So that's really easy to miss. So be very careful. It's like if you were writing on a test like your test number one, you're not just going to indiscriminately change the variable from X to alpha or whatever. So think about that when you're doing the problems and be very vigilant about your notation, okay? So I don't want you to get frustrated thinking, well, I'm doing this right and WebAssign's out to lunch. And, we always have to follow directions. So be careful with that. Now, one thing we can notice here, let's just go ahead and look at this part. For instance, we know that the domains, assuming that this is true, and I'll just go ahead and tell you that it is. Let's go ahead and look at the domain of F. We know that's going to be the range of F inverse. Well, first, we just have to make sure that we don't divide by 0. So of course, this would be all X such that 3X plus 4 does not equal 0. So of course, we can solve that. That's easy. We just subtract 4 and divide by 3. So in this case, the domain of F would be all real numbers not equal to -4/3. So that's a bunch of real numbers. But then, of course, for free, without even computing the inverse, we have the range of F inverse. So a problem might ask you just to compute the range and domain of the inverse function, and you don't necessarily need to compute the actual inverse. You can use the function that's given to you. And then now, of course, this will be something we talk more about when we get to rational functions, which will be soon. We can see that with the -3 and the 4, that the 2/3 would never be in the outcome. It could never be a range element. And I've already talked about that. So this would be a quick way to think of this in terms of rational functions. And another thing I've mentioned to everybody is that if we learn something new, past a particular section, then feel free to use it. I mean, we've been talking about multiplicities of zeros, and if that turns out to be useful in a problem you're working, go ahead and use it. So now the range of F will be all Y such that Y does not equal 2/3. And then, of course, well, I don't need that. We don't have to solve anything else. And so this will just actually be the what? The domain of F inverse. So if we wanted to formally write these in interval notation, we can say domain of F inverse will be all reals except 2/3. And then, of course, the range of F inverse will be all reals except -4/3. So what we see on the first test is just a lot of computational techniques that you mastered in college algebra. and algebra 2 and algebra 1. And so we want to make sure that we're comfortable. Now, the one-to-one, let's just prove just for some review of this. So suppose f of A equals f of B. Does this imply that A equals B? That is, does this imply that the inputs would have to be the same? So let's substitute 2A minus 3, 3A plus 4, and of course this will equal 2B minus 3 and 3B plus 4. So again, probably for the test, the one of the ideas that I'm asking here that would be a really good question would be something like this, where we have domain and range, or the computation of this. I probably want to ask you to do a proof, but knowing the proofs actually help you do the problem. So look for more problems where you actually have an object to compute. So now if we look at this, we can cross multiply. So we have 2A minus 3, 3B plus 4, and then we have 2B minus 3 and 3A plus 4. Now we can distribute. We love the distributive law. Polynomials distribute. That's why we get the linear algebra or the ring. So we have 2 times 3, so that's 6AB, and then 2A times 4, 8A, and then negative 3 times 3B, 9B, and then negative 3 times 4, minus 12. Now I move to the right-hand side. I keep adjusting this because I want everything to be level. So let me see, there we go. See if that's a little bit better. And now we have multiplying 6AB and then 2B times 4. So this will plus 8B, negative 3 times 3A, negative 9A, and then negative 3 times 4, negative 12. So, and of course here I left out my B. That's one thing about mathematics. If you write everything down, it'll say, wait a minute, you left me out. Again, that's why I need to see your work. It's important. And as a future STEM professional, you will have to show your work when you solve problems, and you will have to make a summary or a report of it to your colleagues. So it'll be something you'll do every day. Now notice, we see that some of the terms will just automatically absorb. The 6ABs absorb, the negative 12s absorb. So now let's just collect everything. Let's just write down what we have. 8A minus 9B equals 8B minus 9A. Now, of course, we can just remove all the A's to one side and all the B's to one side. So let's add 9A to both sides, and that'll give us a 17A. And let's add 9B to both sides, and that'll give us a 17B. And now, of course, the 17's absorbed. So it's just what we thought. It is true. F is 1-to-1. Now, again, this is just a good algebra exercise and something that is good to be able to do. Now, the last part that we need to do is, for instance, when I did this and, we just kind of jumped out on a limb and said, oh, okay, we're in good shape here. Believe me, we would probably want to know this. Or if the question just says compute these things, you can tacitly assume that it's 1-to-1, that the inverse exists. So don't stare at it and say, oh, well, I wonder if it's 1-to-1. If I ask for a domain or a range of an inverse function or the actual formula for it, it will exist. This is not a question to confuse you, and not a trick question. Now let's do the last part. For the inverse, we always just say, okay, well, let's just set the formula for F equal to Y, any variable you like, because then, of course, we're going to convert the final equation back to the x variable, because we always think of graphing them on the same set of axes. But again, we just abide by whatever variable is requested in the problem. So now when we look at this, this reminds us of the one-to-one. So if you can do the one-to-one, you can certainly do this. So now we can cross multiply, just like we did before, but we want to solve for x. So this will give us y times 3x plus 4 equals 2x minus 3. So now let's just distribute 3xy plus 4y equals 2x minus 3. So now if we want to solve for x, and you'll always be able to do this with these examples that I ask you to do, we want to make sure we have all of our x terms on one side. So let's just go ahead and remove this term to the left. So we have 3xy, your choice, it doesn't matter, minus 2x. And then just remove the 4y term to the right. So we have negative 3 minus 4y. And if we have a whole bunch of negatives, we can multiply and divide by -1 to get rid of them. That would certainly be legitimate. So now we can factor the x. So we get a 3y minus a 2 equals, and if you like, just go ahead and factor the negative. So now divide by 3y minus 2, and we know this makes sense because we've already computed ranges and domains. So we have the negative of 3 plus 4y, in this case, divided by 3y minus 2. Now, if you wanted, you can multiply and divide by -1. It's certainly not required, but if you wanted to, you could to get rid of that negative. So that'll leave us with a 4y plus 3. And then, of course, the negative here, we'll just flip these around, 2 minus 3y. So now we define, of course, this would be the inverse in terms of the y variable. So we define f inverse of x to be 4x plus 3, 2 minus 3x. So when you look at these particular examples here, the idea is, again, finding the reverse path. What is the path back? Okay, now this notation is nice because we input input x, and then we output a y, and then we're at y, and then we want to go back to x. So when we think about this notation is probably a little bit better because it gives us the circuit. But when we want to think of the functions as independent functions, we write them with the same independent variable, even though this notation is actually better. You had a problem in WebAssign where you did degrees Fahrenheit and degrees Celsius, and you maintained the variables. That is, you started out with C, and then you ended up with F variable. So again, it just really depends on how the problem is stated and how the problem asks you to actually write the inverse function. So there are many ways to think about how you can notate mathematically. So what we do is we make sure we follow the problem. And then, of course, when you look at the answer selections, you say, oh, okay, all of the inverse functions are written in terms of x independent variables. So I need to switch these out, and oh, there's my answer right there. Okay, so again, the inverse process is simple, but it's something that will come up over and over in calculus because, again, you'll talk about functions, then you'll talk about their inverses, and then you want to know how to do their calculus. So these concepts will be very, very important. So that's a good example to start because it gives us plenty of algebra. Now, what I want to do is solve some equations. Now one thing that's really important here in solving equations, you pretty much learn how to solve inequalities when you think about a sign test. So what I want to do is kind of merge into that first. I like the sign test. I like the boundary values. I think that's an extremely important concept and something that you all often ask during the conference hours. So I want to set up a domain question for a function that basically requires a sign test. Now, when I look, for instance, for a particular example, and I'll say, okay, well, once we find the BVs, we we plot the BVs, and then we have a test point. So, for instance, here's an example. Say we have X. I'll do a -1 to keep it simple. So we have an X -1. And then downstairs, I'm gonna throw in a quadratic that has irrational zeros. So we'll say X squared minus, let's say, 3X. And let's see here. So plus, I don't want to make it too simple. Let me do this. Oh, that one finally died. So let's get a new one. Oh, yeah, shipping. There we go. Get the, oh, well, here we go. Let's see if I can get this to resuscitate. If not, I'll try another one. Okay, there we go. Oh, well. Let's see if I can get this to work better now. There we go. So let me get another sheet. Technical issues. This is my lifesaver. So here we go. Solve in R. And we'll have X -1. And let's see here, I'll throw in a 2. So we have a 2x squared. And let's see, we'll say minus 4x. And let's see, so we'll say plus, in this case, 3. So let's see, yeah, that'll work. Now, the reason I wanted to set this up, and then we want this to be, let's say, less than 0, okay? So here's a nice inequality that requires us to be able to factor and solve things. So what I wanted to do here, when you look at the AC, 2 times 3, that's 6. And then you're thinking, well, can I get any factors of 6 to actually equal -4? So when you check AC, you have 2 times 3. And then you're thinking, well, I can throw in a couple of negatives, 6 times 1. Is that going to work? No, that's not going to equal the -4. Throw in 2 negatives here. That'll be -5. So this is not going to work. So one nice thing about this inequality, it's set up, we have our 0. So the first thing we have to do here is check the discriminant to get our BVs. So we'll say B squared minus 4AC equals -4 squared minus 4 times 2 times 3. B squared minus 4AC, okay? So now and these are easy numbers. I won't factor it. I factor everything to death. 16. And now in this case, let's see, is this going to be larger than I need it to be? So this will be, in this case, a 12. Well, actually here we've got an 8 times the 3, so that's a minus 24. And this is less than 0. Now, when we look at this, we think, okay, well, this has no real solutions. So no real solutions. Again, when we look at this, b squared minus 4ac, when I don't factor it, it throws me for a loop. But here's something that's interesting. Let me just show you another technique. We can say 4 squared minus 4 times 6, and then factor the 4. And that leaves us with a 4 minus a 6. So this equals 4 times a negative 2, which is negative 8, which is less than 0, which is the same thing we got here. So either way you want to do it is fine, but there are no real zeros. So now when we look at BVs, we just have 1. That is 1. And so you're like, oh, we love this. Because now what we can see here is this particular quadratic function, and I'm going to do another calculation on it, but this particular quadratic function is always positive, and we'll prove that. And we actually kind of need to. So you're thinking if we substitute 1, we get 5 minus 4, which is 1. And then we're thinking that's got to be a proof, even though it seems kind of feeble. There's no way it could ever be negative, because if it were negative, it would have real solutions. It would have intercepts. So now we just have 1. And then we just do a test point, say maybe negative 3 and positive 3. And all we have to do is check this. So we have x minus 1 over something that's always positive. So we don't even have to write it. That's why I wanted to do this, just to give you a little bit more insight. Now, with the negative 3, again, here we look at this factor, that's clearly negative. So this is negative, so that gets a check. And of course, if it's 0, that's no good. Then of course, with 3 here, this is clearly positive. So that gets an X. So this just implies our solution set will be negative infinity to 1. So when you look at this problem, you're thinking, oh, jackpot, jackpot. No zeros here. Now, of course, no real zeros. Now, of course, if there were real zeros, that makes the problem harder, because then you've got 3 boundary values. So I want you to be aware of that, and maybe we'll try another one similar to that. Now, just as a little bit of practice here, I basically asserted that this function is always positive. And then, of course, you're thinking, all right, I see that. We showed that the discriminant is, in this case, negative, so the zeros are imaginary. And then we check 1 point, and it's positive. So when we think about this, we're like, okay, that's a great way to look at it. Okay, that's cool. So now we're thinking, say we flip this around. Say we flip this around and say, okay, what's the vertex? I mean, if it's always positive, wouldn't the vertex have to be above the x-axis? And you say, yeah, because there are no, or below, and you say, well, it can't be below because we checked a point and it's positive. So let's do this. For 2x squared, just to get some practice, minus 4x plus 3 as a quadratic function. We'll just call this now f of x. And we'll say compute vertex. And so now when we look at this, we're thinking, okay, well, let's just complete the square. So we have 2. In this case, we want to make it monic. We want the leading coefficient to be 1. So we have x squared minus 2x. Again, this gives us 2x squared, and the 2 times the negative 2x gives us a negative 4x. And now, of course, we're going to save some room here and have the plus 3. So I use easy numbers. When I make these up, I try to think of simple numbers so that we're not too occluded with too much arithmetic, but you're good with the arithmetic. So now to get the magic number, we take half of this. So we have the negative 2 divided by 2. We're going to square it, but of course this will give us the minus 1 squared, which is 1. So we add 1 and we subtract 1. Okay? So now when we look at this, we're good to go. Here's our perfect square trinomial. Well, let me put the 1 here. This is our perfect square trinomial. So now we have 2 times x minus 1 quantity squared. Of course, that'll give us the x squared, the minus 2x, and the positive 1. And now we have a minus 2 plus 3. So this gives us 2 times x minus 1 quantity squared plus a 1. So now, of course, this is just a x minus h quantity squared plus k. So if and only if the vertex is 1, 1. And again, we see that the vertex is, as Professor Ron stated, it's above the x-axis. And so the leading coefficient is positive. So A, this is another proof, but a whole lot longer. A equals 2, which is positive. So this implies graph opens upward. So again, that's a proof of this, but this is kind of long-winded. The idea here, and this is what I'm trying to show you as a means of maybe doing a calculus problem later on down the road. If we show that we have a quadratic that has imaginary zeros, then all we have to do is just check a point. Just check a point. And if it's positive, then you know the graph, the outputs exist in the positive realm, the graph is above the x-axis. If it's negative, then the graph exists below the x-axis. And again, never zero. So that gives you the sign that you're going to need when you do these problems. Because of the leading term, okay, will always be positive. Well, yeah, but exactly. I mean, that's true, but that's a little bit a little bit convoluted, but that'll work. I think the in order to actually prove it, you've got to do this or do this. Think mathematics has to pass the litmus test. And so when you look at this problem, then you think, okay, oh, well, I can graph this. So let's just go ahead and finish it and do a quadratic. So now, if we wanted to go ahead and write down the axis of symmetry and all of that, so we have x equals 1 is our axis of symmetry. And now, of course, there are no x-intercepts, no x-intercepts. So we kind of got that for free. And then, of course, the y-intercept will just be what? 3. So y-intercept 3. This is just f of 0. So we can get a cheap graph. And of course, when you're graphing, you know, you figure out some points and you pull in that parabola tool and you go to a point and click on it and then drag the parabola curve to another point on the curve and click on it, and then it automatically draws your parabola. Some of you have had trouble with that, but it does all the work. You just have to know some points on the graph. Usually 2 will work. I usually say do 3 because you really need 3 points to determine a unique parabola or quadratic function. But that's how you do that. So again, on the test, you won't have to do that. You'll just have to draw it if you're asked to do it at all. And so now we've got our 1, 1 as our vertex. So I'll spread things out a little bit. And then we have our y-intercept. So we have vertex 1, 1. Now, if you like, we can just use the axis of symmetry to get another cheat point. Oh, this eraser tape is getting all over me. I can remember the first time I used the eraser tape, I thought, oh, this is magic. Now I get boxes of 10 from Amazon, x equals 1. And now we can use the axis of symmetry. Again, we've got the point here. We can go the same distance on the other side to 2, 3 right here. Just using the axis of symmetry, 2, 3. And here's 0, 3. And so now we can draw it. Just using our little parabola tool, which is Professor Ron's blue pen. Again, not Rembrandt, clearly, but just reasonable. So on the test, you might have some pictures of some graphs of quadratic functions, and you would have to choose the correct one. So when you do your test work, you've got to draw everything and work out the problem. And then when you choose the correct selection, you look for the responses that mimic what you have done. So again, when you look at the problems on the test, okay, work it out just like you're doing WebAssign. Work everything out and clean it up and say, okay, I've got that one, or these are rewritten a little bit. They're simplified a little bit. Let me do a little extra algebra. There we go. It's this one. So again, work the problem just like you're doing a WebAssign problem. Give me plenty of detail. So one thing that we can notice in this particular case, these problems have all kinds of interesting ideas. So say, for instance, we had a question posed this way. For instance, here's an example. Say we had compute the minimum of f of x equals 2x squared minus 4x plus 3. Compute the minimum. Okay, well, I mean, say we didn't do all of this other stuff. Well, you have 2 options at this point. You can say, well, I can complete the square and the k falls right out. So that's one way to do it. Let's try another way. Now, of course, we don't have any x-intercepts, so we can't use the midpoint, which I used to solve all of those problems with the applications. Now, what's funny is in Calculus 2, we were doing an area computation, and I said, oh, let's get the vertex, let's do the midpoint. And they thought that was interesting because they'd never seen that before. But I told them, I said, we just need to figure out the region. Maybe the vertex is not that important, but I said, let's just review. I said, my pre-cal students know how to do this, and they thought that was interesting. So now when we look at this, let's just look at this in another way that might be kind of simple. Say, for instance, thinking, well, I'm just going to knock this out. I'm just going to do the formulas. First, you're going to say this makes sense because A equals 2, which is positive, which implies absolute minimum. So at least this makes sense. Now, of course, with the applications, we didn't always want our function to become arbitrarily large. So most of them end up opening downward. So there's a maximum. So there's maybe a reason for that, at least with the types of problems we were solving. And so we can say, well, A again is 2 and B equals -4. And so you think, well, H will be the opposite of B over 2A. So we get the opposite of the opposite of 4 divided by 2a, which is 2 times 2. So this gives us a 4 over a 4, which is a 1. So that's our h. And so we've got that. Again, we already knew this, but we're not thinking that we've actually done the previous exercise. And so now we'll say k equals the minimum. And this will just be f of 1. Now, of course, when the numbers are user-friendly, that's fine, but completing the square is really very useful because it's easy to do and falls right out. But here we go. So we have 2, 1 squared minus 4 times 1 plus 3. That is when the numbers are user-friendly as they are here. So we have 2 minus 4 plus 3. So this gives us a negative 2 plus 3, which is 1. And we have the minimum value. So a problem may just say, okay, well, find the vertex, find the x-intercepts, or find the minimum, find the maximum, things like that. So with the quadratic function, now that your master's at it, just remember, you have 2 forms. You have standard form 1, which looks like the quadratic equation, ax squared plus bx plus c. This is the number 1 form. And then you have the number 2 form, which looks like this. Again, we still have the leading coefficient like we do complete factorization, but we don't give the factored form. Like for instance, you're thinking, do I just write this as a product of 2 binomials of degree 1? No, we say, just like we've done up here, x minus h quantity squared plus a k. This is the number 2 form. So when the problem gives you this, and then they say write the quadratic function in standard form, they mean do this. I mean, you don't type this again. I mean, I guess you could say that's a standard form, but obviously the problem wouldn't be asking you just to type the same function. So when you're given this and they say write in standard form, then they mean this. WebAssign means, okay, go ahead and give me the second alternative. So again, with quadratic functions, we shouldn't really ever complain about them because there's nothing that we can't figure out about them. And again, like I said before, using multiplicities and using all the tricks that we've already figured out now, moving on into polynomials, you are more than welcome to try those out in some of the problems that you do for the test. So good mathematics is good mathematics. And if it supports your answer or your response, then that's exactly what you need to do. Now, here's an exercise that I actually did in the, there was one that I did in the conference hours that I want to do. It was, and it's, you'll remember this from your WebAssign. There are actually several of these, but I want to do this one. And then there's another inequality. Inequalities keep you busy, obviously. So here's the example. Here's a standard mixture problem. And this says, here's what we have. We have 120 gallons of 4% bleach, kind of like the radiator problem. I remember when I was doing this for the student, I said, oh, this is the radiator problem. It was an excellent example. And we need 120 gallons of 6% bleach. So unlike the radiator problem, we don't want to make it more dilute for the summertime driving. We want to make this more concentrated. Maybe we need to clean the the restrooms are the place where we work or something, or, you know, due to the COVID protocols, we need, you know, stronger solution. It's kind of like when you live in Houston, mildew is a problem. When I go to Montana and visit my sister, she's all environmental. And I said, Kim, the kind cleaners don't get rid of the mildew. And she says, well, you shouldn't use bleach. I said, well, Kim, then I'd be overrun with it. And so she laughs at me and we laugh and whatever. But you know, living in Houston, that's a problem. I've talked to students whose parents were in the construction business, and if they didn't keep their construction airtight, then mildew would take over, and they would have to just tear the building down. So we can identify with this problem. So when you look at this, you're thinking, okay, so what's the question here? How much pure bleach do we add? That is, we need to take away some solution and add pure bleach to make it more concentrated. So determine the volume of 4% bleach that must be, I'll rephrase this, that must be replaced with pure bleach. So the idea is just like the radiator. We want to take away some and either make it less concentrated or more concentrated. So with the radiator problem, we added water, which had no antifreeze in it. So here we're going to add pure, in this case, pure bleach. So we can say so now we're ready. You know, we wrote this in our on our separate sheet of paper from the problem. And then we say, okay, pick a variable because Professor Ron has to know what you're doing. So let X equal, choose either one. We'll just say volume of pure bleach. Pure bleach. I'll make sure that's a U. Pure bleach. And so now we think of, okay, so what's the mixture process? Now we're mad scientists. Well, the goal is the 6%, just like I taught you. And we know that has a concentration of 6/100 with the bleach. And of course, the goal, again, is 120 gallons. So that's the easy part. Now we're thinking, all right, so pure bleach, that's 100% bleach. So that percentage is 1 or 100/100. And then we have X gallons of that. And then whatever we drained here must be shown in the volume of the 4%. So we have 4%, and then we have 120 minus X. And I remember the students saying, oh, that's the key, the minus X. So you always have to think about what you're getting rid of so that you replace with what you need. So that probably is the only kink. And when the student said that, I thought, you know, this is good. I've done this before, but maybe we need to review this. These make great test questions. So now you're thinking, okay, well, this is a nice problem with fractions in it, and we can get rid of all the fractions just by multiplying by 100. So now what I want to do, go ahead and write the problem away from the blanks, just so you can more easily see it. And we'll just let the numbers do the work for us. So again, you know, go ahead and multiply by 100 to retire all those 100s. So now the 100s absorb, and we get 4 times 120 minus X. And of course, here this 100 absorbs, and we're left with 100X. And here, of course, the 100s absorb, and we're left with 6 times 120. So what do we have over here? We have 4 copies of 120, and we have minus 4 copies of X plus 100 copies of X equals 6 times 120. So now we see, okay, well, we can take 4 copies of 120 from 6 copies and get 2 copies. So 2 times 120. And then of course here we've got what? 4 copies from 100. So that's 96 copies. Now, this is where I told the student, I said, we can be a little bit more clever and say, okay, well, let's retire a few numbers. Let's just go ahead and write this as 2 times 2 times 60 and maybe get rid of some of the numbers. And so now, of course, that's a 4. So 4 into 100 is 25. So this will give us a 24x. Just make the numbers a little smaller. And so we just have 4 times 60. And so now we can retire the 4s. So we have 24x equals 60. And now we can keep going if you like. In this case, 4 times 6 times x. And this is just 6 times 10. We'll just make the numbers as small as we can so we don't have any work to do. So the 6 is absorbed. And we just get 4x equals 10. And so now we'll stop. So x is 10 over 4, or 5/2. So the reason we let the algebra do the work is so that we don't have to do any extra computation. And I thought this was an interesting problem because now the student said, oh, I see, Professor Ron, the answer is 2.5 gallons. And so now with your WebAssign, rarely do, for instance, you'll do fractions a lot of times, but when you're just giving an exact answer, it's sometimes more convenient to write it with the exact decimal. And so in this particular case, we could just say 2.5. So we'll say add 2.5 gallons of pure bleach. All right, and that means we've taken away 2.5 gallons of the 4% solution. So again, this is a technique, and it's a popular technique. And if you can do this one, then you can do any problem. I mean, it's just like this. This is the type of problem that kind of sets you up for any mixture problem. So I thought this was a good example. Now, one other example that I did on that particular day that I thought was really good was an inequality. And before we do that, let's just go ahead and do another word problem. I've got an old test here that you have on your blackboard. And here's a nice example. This is a time, rate, distance. So we'll get back to the inequalities, but let's do another word problem. So example, this says a motorboat, I have one like this in the Smart Pen videos. A motorboat travels 15 miles per hour. And well, I'll just say 15 miles per hour in still water. Okay, so basically there's no current, but we're going to figure out the speed of the current. Then it says the boat travels 12 miles upstream, 12 miles upstream, and then returns. The trip time is, well, back to that number again, 5/2 hours. And then it says compute the speed of the current. So when we think about this, we're like, oh, this is time, rate, distance. And you all are great at time, rate, distance. But I thought this was kind of an interesting problem, the way it's set up. And then you're thinking, well, it seems fairly straightforward. How do we do this? Well, we need time elements because we know the times can be summed to equal this. So what we can do, if you will, and we don't know the speed of the current. So the first thing we can say is let X equal the speed of the current. So this would be our declaration of a variable. And so, of course, we've got the upstream, and then we have the downstream. The way that I organize these problems has to do with a technique, like I told you before, that I set up when I taught the intermediate. My colleague, Nate Wiggins, and I both, I told you before, started out doing half and half. And we didn't stay in college prep. We basically got kicked out. But it was basically because they thought we were too challenging, but it actually turned out that that was incorrect because our students did well that worked. And so when I taught them, I developed these techniques and they turned out to be very useful, and I still use them. So thanks to those students, they made me a lot more creative. So now let's just go ahead and do our little chart here. So we have time, we have rate, and we have distance. Now, when you look at this, you're thinking, okay, so in this particular case, when we go upstream, the current is working against us, so it's subtracting from our rate. So we have 15 minus X. And then when we go downstream, we're going with the current, so it's assisting us. So it's adding to our rate, 15 plus X. And now in both cases, the distance, so we go upstream, we go downstream, the distances are equivalent. So remember, D equals RT. Now, when you look at this part, again, we have a setup where the time, the trip time, gives us the entire journey. So there's one other thing that I wanted to mention that I had written here. Oh, yes. Notice here that we have the boat travels 12 miles upstream and then returns. So we've got a distance in both cases that's equal. And I wanted to check to make sure that I'd actually written that, and I did. It's right there. So we have 12 and 12. That's consistent. And so now it makes sense to solve for T. T is just D over R. And so now we can fill that in. I thought, well, I haven't given them enough information, and I did. And then we have 12, 15 plus X. So this gives us a little practice with the least common denominator approach. Again, very basic, but doable. So now what does this imply? Well, the trip time is 5/2 hours. So we'll say time upstream plus time downstream. 12 over 15 minus X plus 12 over 15 plus X will give us the total time, which is 5/2. So now this equation right here would just be a good test question. So the time, rate, distance problem actually focuses you on solving certain equations that we can write in a simpler way. So now we look at this and say, okay, LCD will be the product of all of the distinct factors. So we have 15 minus X, 15 plus X, and then times a 2. Now, one other thing that's kind of convenient here that we might want to notice as we work through this is certainly going to be one way we write it, but now we can see this is a difference of 2 squares. So this is 15 squared minus x squared times the 2. And if you will, this is just 225 minus x squared times 2. So that might be just looking at this, that might be a little bit more useful way when we consider what happens over here when we combine terms. So we've got 2 ways of looking at the LCD. So now let's go ahead and multiply. So we have 12 over 15 minus x. I'll go ahead and write it again so we preserve the original equation. So we have 5 halves. So now multiply by the LCD. And this is on this side where it'll be convenient. So since we don't have any x's over here, I'm going to use this form for this side. So this will be 2 times 225 minus x squared. Sometimes that do a little extra work and you make it a little bit better for certain components of the equation. And now, of course, here, we'll just use this form. So we have 15 minus x, 15 plus x times the 2. Kind of squeeze that in there. So now when we look at all of this, we now see that we retire the 15 minus x, and then of course we have a 2, in this case times the 12. So that's a 24, 15 plus x. And now here, notice the 15 plus x retires, and we're left in this case with the 2 and the 12 and the 15 minus x. So we have a 24, 15 minus x. Now on this side, the 2's absorb, and we're left with a 5, and we'll go ahead and multiply it out. 225 minus 5x squared. So now if we look at all of this and we think, okay, well, some things hopefully will retire, let's go ahead and multiply this out. We have, in this case, a 24 times a 15 plus a 24x. Then we have plus a 24 times a 15, another copy of that, then minus a 24x. So these will absorb. And this gives us 5 times 225 minus 5x squared. So now when we look at all this, we can retire some more numbers. So let's put all these together. So we've got 2 copies here. So let the algebra do all the work for us because we're lazy. We'll have 2 copies of 24 times 15. Now, of course, we've got a 5 here, so we can write this as 5 times 3 and absorb the 5's. I'll go ahead and factor that. So now the 5's go away, they absorb, and we're left with 2 times 24 times a 3 equals negative x squared plus 225. Now, when we look at this, we can run everything over and the x squared over. So we'll do x squared. And then we have 225. And now notice here, this is just minus a 6 times a 24. So equivalently, we have x squared equals 225. And now notice here, we've got some 3's in here, but I'll just go ahead and multiply it out since it'll be easy to do that. So we get a 4 and then a 2, so that's a 144. And now when we subtract, we get a 1. And then of course here, we get a 12, so that's an 8. So we've reduced our equation to a simple square root property. If and only if x squared equals 81. Now notice, just like I did in the previous problems, all of these numbers work out nicely algebraically. And then of course here, you're thinking we've got 3's in both of these, and I could have factored the same thing here, but these numbers were relatively easy to work with. And so now by the square root property, x equals plus or minus the square root of 81. So x equals plus or minus 9. Now, of course, the negative we discard. So discard -9 because it's not relevant here. And then, of course, x is actually the current speed. So we say this implies the speed of the current is 9 miles per hour. So again, what I liked about this problem is that we kill like 4 or 5 birds with one stone. When you look at this, not only do we have modeling, but we have the equation solving technique. So we do the LCD technique. So this kind of gives us additional work with that. And then of course, we just have basic computation of symbolic manipulation. And then of course, we basically end up with the simplest kind of quadratic that we all like, no constant term. And that just gives us the square root property. And so we're good to go. So again, use the word problems as a way to review techniques concerning equation solving. Sometimes they're not, maybe on the test, you'll have a similar problem. Maybe all you'll have to do is cross multiply. It just really depends on how things are given. But I like this particular example because it showcases a lot of techniques that you will continue to use. Now what I want to do, again, we've done the mixture. I want to do a time rate, a fraction of work. And I've already done the tanker problem. So there was another example from the office hours that I thought was really good from your WebAssign. So let's look at that. So here, this example has to do with the job is basically filling a pool. So we'll say job, in this case, filling a pool, like a swimming pool. And so Bob and Jim both have it's like you go to this house and they've got a yard hose, and you go to this house and they have a yard hose. And we know in this particular case what they can do with filling the pool. So we'll just say together, this is part of the hypothesis, job in 18 hours. So if they work together with both hoses, they can fill up the pool in 18 hours, which isn't that bad when the garden hose isn't going to do much work. And then in this case, we say Jim, and there's an additional here. It says working alone, Bob completes the job in half the time, required. And the other guy's name is Jim, for Jim. Working alone, Bob completes the job in half the time required for Jim. So this is where we set up our variables. So we say let, in this case, T equal the time for Jim. So now we can say, in this particular case, Jim, job in T hours, and we'll say job in half the time, 50%, job in T over 2 hours. So this implies 1 over T, in this case, fraction of the job per hour, and this says 2 over T, fraction of the job per hour. We did that other problem where we had 3 people and we ended up with a quadratic equation, but it was done the same way. So now it just says, you know, compute the time for each. So so in this case, we'll just go ahead and see how long it takes them working individually. So that's easy. So now we can say, all right, okay, 100% of the job with the technique I give you is 100 over 100. And then of course we have Jim's contribution and we have Bob's contribution. And we know the fraction of work per unit time that they both input, and then we know how much time it takes when they work together. So that completes the equation for us. So for Jim, we have 1 over T, that's the fraction of work per unit time. And for Bob, it's 2 over T. And then of course, they both work for 18 hours. So with this particular problem, we can figure out how long each of them work individually. So now we have 18 over T. I thought this was neat because it reminded me of the problem I did in class. And then we have, in this case, 2 times 18 over T. Now, when you look at this and you think about this, this equals 1. So if we look at this, we're thinking, well, this is so much simpler than the last problem because the denominators are the same, so we're good to go. So now we'll just say T, and we have 18 plus 2 times 18 equals 1. So we can reciprocate and we'll be done, but let's just go ahead and write it out. So this will be 18 times 1 plus 2 over T equals 1. So in this case, we can just say this is what 18 times 3 over T equals 1. And then of course we can multiply that out. That'll be a 4 and a 2. 2 plus 3 is 5. And then reciprocation or cross multiplication, T over 54 equals 1. So T equals 54. So now this implies Jim, job in 54 hours. And then Bob, job in 54 over 2 hours, which in this case will be 28 hours. Oh, excuse me, 27. Oh, how sad. 14 over 2 is 7. The math never fails us. We failed the math, but the math never fails us. So I thought this was, again, an interesting problem. That particular day, we did lots of word problems, and I know the word problems can be difficult for you, just because you don't really do them all the time, and of course you're not going to end up doing these forever. There'll be more types of calculus problems that you do in optimization, and those will be interesting and challenging problems. But having done these types of examples will certainly make you better at doing them. Okay, so now there was one other inequality that I thought was really, really good that I worked on. Let's see here. Yeah, this one was what we always like the ones that have the challenging numbers. And so I'll save that. So I'll put that aside and have that to do. But I wanted to mention a composition and then just a word type problem with a quadratic. So just to remind you about this, here's a factoring example. say, I'll just say factor the expression. So this is like a calculus expression. And when we say factor, basically simplify. And you can think if we factor an expression, maybe we're trying to set it equal to 0, which would be something that would be useful. So here's an example. Say we have something like this. So we'll take, in this case, say x plus 2, in this case, to the negative 5/3, and we'll say plus x plus 2 to the negative 2/3. Okay. So that seems like, well, what do we do with that, Professor Ron? I don't know. What do we do with that? Okay. So lots of you look at this and say, well, I don't know what to do with this. And I've taught you this technique. And when I give you a problem like this, the first thing I say is that, well, you can get rid of the negative powers and write everything as fractions, get a common denominator, and get the same answer. But the technique I was showing you, because it occurs a lot in mathematics, is do the factoring technique, where we extract the least power of the base. In this case, it's negative 5/3. Okay, and this happens a lot with calculus because of a theorem called the power rule, and it'll be a power rule for derivatives and also for antiderivatives. And because it occurs so often, this technique I'm teaching you is worth knowing. So you're thinking, well, there's nothing here. So let me just kind of spice it up a little bit. So as an additional problem, we'll just say solve in the real numbers right here. Just solve in the real. So let me just throw that in. So say you really had to solve an equation and you're like, oh, I don't know what to do. So that's when then you really think you want to simplify this. So when we look at this, we've only got one term and the least power of it is negative 5/3. So we're going to factor that. So we're going to say x plus 2 to the negative 5/3. I remember a student said, oh, I need to figure out what goes in the bracket. So I thought that was kind of interesting when the student said that. So when we factor all of this, we're just left with a 1. But now we're thinking, okay, in this particular case, what do we have here? So we need to be able to get the negative 2/3, but we've got a negative 5/3. So what do we add to negative 5/3 to get negative 2/3? Well, basically 3/3 or 1. So we say x plus 2 to the first power. Again, note 1 plus negative 5/3 equals 3. Just think in terms of fractions, is negative 2/3. So this is what we've done a lot of times. And it's just a matter of dealing with the fraction. So I threw in some thirds here. It doesn't matter what it is. It's just, we see they differ by 1. And so now we're thinking, okay, well, this is easy and I can move this downstairs. So we get x plus 2 plus 1 plus 3. And then downstairs we have x plus 2 to the 5/3. And now, of course, when we look at this, we're like, okay, well, this is simple to solve. This fraction is 0 when the numerator is 0. That's how we do BVs. So we'll say if and only if x plus 3 equals 0, if and only if x equals negative 3. And so that would be a solution in R. So again, depending on the complexity, you may get a couple of solutions. Maybe you'll end up with the quadratic or whatever. But because of the power rule in calculus, these kinds of expressions occur a lot. Now, I'm saying this now. I don't say it at first because then you're like, calculus, what's he talking about? So The thing is that I don't mention this just because I'm just trying to keep you busy. You will see this occur in calculus. And this technique will be of use to you. Again, you can retire the negative powers and do common denominators. Your choice. It doesn't matter. It's just that because this occurs so often that it's worth it to look at it like this. So when we think of fractional powers, it's like doing fractions. You know, we get a common denominator and clean things up. So be able to add those fractions. I did a lot of that in the review or in the lecture. So with that in mind, let's do another one with some rational expressions. So I think what we're seeing here is that our work is getting a little bit more focused because now that we're into the polynomials, we're more concentrated on one thing. So maybe it's a little bit easier. So here's an example. I'll just do another simplify. And here's what's given to us. We have x squared plus 3x, easy factoring, but still a good problem. And we have x squared minus 3x minus 28. And then we're multiplying by 7 minus x and 7 plus x. So you're thinking, okay, well, no big deal. We'll just try to absorb some factors. The idea here is that when we absorb factors, we're looking at, oh, here we go. I like to see your comments. Let me just say this, ladies and gentlemen. Division by zero is not defined, and you still don't believe that. Division by zero is not defined. And so be careful. Don't put yourself in a situation where you're stating mathematics that is false. So when we say simplify here, we're thinking, okay, well, maybe we can factor these quadratics and maybe absorb some of the common factors if they exist. So let's do it. So this is just a little simple exercise, but I want to get you thinking about working with this. So now, of course, here we have the negative 28. So we can say AC equals negative 28. And then we'll just say 7 and a negative 4. That'll give us the 3. So we have x minus 4 times x plus 7. Well, that's useful. And then, of course, here, again, we've got AC equals negative 28. So now we're going to do negative 7 times 3. And that'll give us, well, in this case, 3. Got 3 on the brain, right? So 3, just switch the negatives. Math is so rewarding. And so now that gives us the negative 3. So that's a check. So we have x minus 7 times x plus a 4. So that's just kind of smoke and mirrors, right? So now we're thinking, okay, this is good. Let's get creative. We can extract a negative from this. So we can say, right, think of this as negative 1 times x minus 7. Just rewrite the 7 minus x this way. And then, of course, we can just write 7 plus x as x plus 7, if you will. No big deal. So we're just trying to eradicate the common factors and let them absorb. So now we see absorb. Then we have absorb. The student was saying, yeah, get the B right. Do not on your papers put slash lines. If you put a slash line in your work, I'll put a 0 on your paper. I have never used a slash line, and I mean that. Put a box if you like, underline. Do not put a bunch of slash lines in your work. I do not teach that way, and that is horrible, horrible notation. And I don't know why it's been taught to you, but do not do it, and do not test me. Because as I am talking to you now, I'll put a 0 on your paper. So do not impress me with slash lines. And do not do calculus in my class that I have not taught you, because you may have had an AP calculus course. You are in this class because you need to prepare for a college level calculus course, which is very different. So now that I've said my piece, we're good to go. So we've got x minus 4, and we've got a -1, and we have an x minus a 7. And then what's left here, again, everything, we just got the x plus 4. So now if you like, you can just go ahead and move things around. Now, of course, the x minus 7 absorbed. And so there's nothing there but a 1. So let me make this a little bit smaller. So we're just left with these two guys. And so if you want to flip this around, this will just be a 4 minus x over an x plus 4. Okay, so again, very simple problem. I think I made it harder than it was, but the idea here is just what you do in any kind of like algebra 1, algebra 2 problem, just cleaning things up, factoring, making it look a little bit more simple. Okay, so good. You'll have some problems where you get common denominators like we've been doing, clear fractions, invert and multiply, just like we've done. Of course, I'm going to test you on that. Domains, inequalities. Now, I wanted to say something about, let's see, I want to do that, another inequality, but I want to throw in a little bit of absolute value here. And then I want to say something about just maybe some more equations. So here we'll say solve in R. So let's throw in some absolute value. So say we've got 2x minus 3 in absolute value. And let's see here, we'll say plus 5 equals 8. And then we'll throw in a 2 here, times a 2, okay? So the idea here is that we've got kind of a cluttered equation, not overly difficult, because you know what a conjunction is. And so you're thinking, if you want to clean this up, and maybe you're thinking, well, we want something like x in absolute value less than a c. So let me go ahead and put in a inequality so it's actually challenging. Let's do this. So we're thinking maybe we'll get that, or possibly we'll get something like this. This being the conjunction, and this being the disjunction. So we're thinking, if we need this form, we've got to declutter this. So let's go ahead and subtract 5 from both sides. So we have 2 times 2x minus 3 in absolute value is less than 3. And so we're thinking, well, we're getting close to this one. So it looks like we're going to get the conjunction. So we need to divide by 2. So we have 2x minus 3 in absolute value is less than 3/2. And so this is the conjunction. And we proved this. And we know that we sandwich the argument here between what? -3/2 and +3/2. This is our positive number, and this is our new expression that has replaced the x. So equivalently, we have -3/2 is less than 2x minus 3 is less than 3/2. And so now we're thinking, okay, now this is a compound inequality. So let's add 3 to both sides. So we have 3 minus 3/2 is less than 2x less than 3/2 plus 3. So let's do a common denominator. So we have 2. So this will be a 6 minus a 3. Again, in this case, 2 times 3 is 6. And then, of course, here, common denominator. 2. So we have 3. 2 times 3, 6. So this gives us what? 3 halves less than 2x less than 9 halves. And now, of course, we finish off by dividing by 2, again, a positive number. So everything is maintained. So divide by 2. So this will be 3 halves divided by 2, which is 3/4. And then, of course, 9 halves divided by 2, invert and multiply. So 9/4. Or open interval 3/4 to 9/4. Now, of course, I've said a lot about absolute value, and there's not a whole lot of focus on absolute value in this test. Basically, just word problems, solving equations, working with inverses, compositions, just find the domain of a composition type things. Very straightforward problems. And of course, the only additional thing like we see is we might have to think about some irrational zeros that are actually come up with quadratic equations. So just to kind of remind you of what we've talked about with absolute value, that'll be something that will come back over and over. And we'll always have this nice expression, the square root of x squared by definition is the absolute value of x. That's one of our alternative definitions that we'll find much use for. It's important. You see that a lot in calculus too, when you deal with arc lengths of curves. So that'll be something that we'll see a lot more of. So maybe you'll be happy that I don't put everything possible on the test. Now, I wanted to work an example, another inequality, because those are kind of the most busy type problems that we have here. And this was a good example from your WebAssign, but I just want to modify this a little bit. So let me give you an example of a quadratic equation from an old test that actually has real solutions. And so let's see here. Okay, well, that's in the complex numbers. So let's look at this. So I want to say solve in R. So this is going to be a substitute for that inequality for my conference hours that I think will do you good for the test. So in this particular case, let's do another one. I'm going to build this and kind of take you along with me so it makes sense. So I'm going to have the same factor here. I'm going to have a 2x squared. And now I'm going to change it up just a little bit. I'm going to do a minus 5x. And now let's see here. So we've got 4. I want to do this so we get some good numbers here. Let's see here. Let's do this. So let's see. Yeah, that'll work. Let's see. But I want to make sure that I have, let's see, maybe I'll make this a little bit smaller. Let's try this, see if this will work. So I don't want it to factor, so let me run this up a little bit. Let's see here. So here we go. I want a reasonable. So let's see, that'll be a 6. So we could do a, yeah, and that'll factor. So let me try this. There we go. So now when you look at this, you get a 3 times a 2, which is a 6. So let's just kind of look at this. We have AC. This is how you manufacture real solutions that aren't rational. So we have an AC, so that's going to be 3 times a 2. And then we're thinking we need to get a -6. Well, we could, that throw in 2 negatives, that's not going to work. So we could do maybe a 6 times a 1. And that's not going to work even if we throw in a couple of negatives. So this doesn't factor. And now what I'm going to put upstairs is, again, let's just say we have an x minus a 1, okay? So now let's solve this, and we'll do the same thing. We'll say this is less than 0, okay? So we manufactured irrational zeros, but in this case, notice the actual zeros will be real as opposed to imaginary. So let's do the discriminant to get the BVs. So here we have a -6 quantity squared minus 4 times 3 times a 2. So again, there's a 6 here. So let's say this is 6 squared minus 4 times the 6. So this gives us a 6, 6 minus 4. And so in this case, we get a 6 times a 2, which is a 12. So basically 36 minus 12, or minus 24 is 12. And this is, you know, reasonable. So this is what? 4 times 3. It's not a perfect square, but I rigged it so at least we'd have a irrational zeros. So now we have BVs. So we've got x equals the opposite of b, which is 6, plus or minus, and now we have 2 root 3. So again, remember, we take the square root of the discriminant, so that'll be 2 square root of 4 times square root of 3, divided by 2a, which is 2 times 3. So this will be, in this case, we can go ahead and retire things. This is 2 times 3 plus or minus 2 root 3, 2 times 3. So now all these 2's absorb because they're in all of these. So 3 plus or minus square root 3 over 3. Lots of 3's, right? So look at that and make sure that makes sense. So when we think about this, we're thinking, oh, okay, how interesting, Professor Ron. So now we're going to think about this symbolically. So when we look at this, we're thinking, okay, now when we check this out, again, the 2's absorb and all the nice things happen here. So we're thinking, okay, well, where do these live? So we've got 3 plus square root 3 over 3, or 3 minus square root 3 over 3. So now if you want, we can be kind of creative here. We can say, well, this is approximately 3 plus 1.7, square root 3, we'll just use 1.7 over 3. So this will be a 4.7 over 3. This is bigger than 1, okay? And then here we'll say this is approximately 3 minus 1.7 over 3. And this will, in this case, we have a 1.7, so that'll be a 1.3 when we subtract over 3. Now notice what we have here. We've got numbers that are both bigger than 1. This being, in this case, smaller. So now when we do our BVs, we have 1. I'm just going to call this alpha 1 and call this alpha 2 so I don't have to keep rewriting it. I'll put it on the number line. So we've got what? I'll go ahead and write it anyway. And we have 3 minus root 3 over 3. Okay, so again, when we estimate here, notice these are all positive numbers. These are all positive numbers. So now when we do our BVs, we have 1. And then the next biggest one, put a little space here, is going to be 3 minus root 3 over 3. And then space it out a little bit more. The next one's going to be 3 plus root 3 over 3. All right. So now this is what I'm talking about. When you have a situation like this, the complexity is a little bit higher, but it's still multiplicity one. Notice all these zeros here have multiplicity one. There's one of these right here. There's one of these and one of those. They're all multiplicity one. So now what I want to do is write this in a factored form. So let me get a little bit of extra room here because I kind of squashed that together. This is a nice exercise, and I like problems like this. So now when we check this out, we say the factored form is going to be x minus a 1. And then of course now we'll have a 3, and we'll have x minus 3 minus root 3 over 3, complete factorization, which we're going to do review, but I've done this before already. And then x minus 3 plus root 3 over 3. Now, what we can do is we can cheat because all these have multiplicities 1. So when x hits, the curve hits at that 0, it's going to have to cross. This is 1, 1, 1. This is what I was talking about. And so now let's take a point like -10 down here, and we'll take +10 up here since they're really easy. So let's check. So if we do the -10 here, let's check the sign. This will be negative. -10, again, very negative because these are big negative. And then -10 here, again, negative. Overall negative. So this is a plus, but notice we're down here and now we're done. These are all multiplicity 1. So we're going to say below, above, below, above, and we're done. Because they're all multiplicity 1. You don't even have to check these signs. I developed this technique several years ago because the students were like, oh, they're sitting there punching on their calculators forever. Oh, Professor Rod, I'm going crazy. I'm like, no. Let's use the multiplicity. So again, we do the -10. This will be negative, -10, a whole lot less than this in absolute value, negative, negative. 3 negatives, negative. So below, cross, cross, cross. So now we see where are we negative? Check, x, check. So now when we solve the problem, this implies, where does x live? Well, -infinity to 1, union, this is neat, 3 minus root 3 over 3, comma, 3 plus root 3 over 3, and we're done. So this is what I'm talking about with symbolic computation. Let me just review this. And so let me kind of, so you can see all of it, but I'll pan it back up if you need this for your notes. I started out with an easy one. I gave you a imaginary 0, so no work to do. You had 1 BB, very simple, but still an important problem because it gave us a nice quadratic function problem. So we look at this and say, okay, well, if I'm going to solve this, I've already got the 0. I need to make sure that I have all my BBs. What does BB mean? What does BB mean? What's that abbreviation for? Anybody? Oh, Professor Ron, I know it means boundary value. Okay. So why do we care about the boundary values? Because those are points on the real line where the expression can possibly change sign. And we need to know that. But notice, when we look at this, AC doesn't work, so we do the discriminant. So we do b squared minus 4ac, -6 squared minus 4 times 3 times 2. So that basically gives us 36 minus 24. Of course, I factor everything to death, which is a 12. That's 4 times 3. Now we use the quadratic formula, the opposite of b. plus or minus the square root of the discriminant, which is 2 root 3 divided by 2a. And now all the 2's absorbed, leaving us with a bunch of 3's. Yay, it makes it easier to estimate. So now what we see is when we estimate these, we've got all of these numbers that are positive. They're all bigger than 1. In this case, oh, my goodness, I kind of cheated a little bit. This is bigger than 1, but this one isn't. Oh, forgive me. I know you all probably saw that. Let me just kind of rearrange this. It's going to change the solution set. Sorry. Let me just move this around. Just move these two around. Ugh. That's why I went back over this. So this is clearly less than 1. So we'll put the 1 here, and we'll put this one here. So this will be 3 minus root 3 over 3. It's not going to change the solution set except here. So now this will become a 1. I'll explain that. I went kind of fast through that. So that's a 1. Sorry. Yeah. So now notice my little adjustment here. This number here is less than 1, but greater than 0. So again, we have a 0 down here, which is not a boundary value. So this number is less than 1, and this number is clearly bigger than 1. So yeah. So in this case, we say less than 1, add that to your notes, and we say this is bigger than 1, but it doesn't change the multiplicities. Okay, so good. The math does not forsake us. Now we say, what are the BBs? Well, let's look at all the zeros. And now we've got the order right. We've got 3 minus root 3 over 3, which is greater than 0, but less than 1. So it's here, 1. And then the irrational number that's bigger than 1 right here. Okay? And they all have multiplicity 1. So every time when we think about the graph of this function, when it crosses, hits an intercept, it's going to have to cross. So we do the easy part. We do -10, and we say, okay, if we input -10 into all of these factors here, we got the leading coefficient of 3, we get negative, again, negative, negative. 3 negatives is a negative, so we're below. So then we can use multiplicity 1, cross, cross, cross. Where are we below the x-axis? From 0, negative infinity, to the first one, and now I can change this one to the right one too. How funny. Math, we will forsake the math, but the math won't forsake us. We forsake the math. There we go. There we go. So now what we see is that we're less than 0 here, negative infinity, to the first 0, which is 3 minus root 3 over 3. So that's a check. As we go from this irrational 0 to 1, we're positive, so no good. But then from 1 to this 0, we're negative, so we're good. So let me make that look a little bit prettier, 3 minus root 3 over 3. So we have 3 minus root 3 over 3. So the thing is that the symbolic computation makes this problem doable. And here's another thing. This is what I'm talking about. When you write your work down, then you know what you have. And I looked at that and said, oh, that's bigger than 1. So I looked at the 1.3, maybe my brain thought 13 over 3. Okay, that's clearly less than 1, but it's between 0 and 1, and this is clearly bigger than 1. And so now when we order things, this comes before this, but the multiplicities are all the same. And so now below here and below here. So I would look for something like this on, I would say on our test where you've got some irrational zeros where you could use this technique. I think this is something that I've been trying to teach you from the very beginning, that if we do symbolic computation, then the algebra will reward us. We may possibly make some incorrect deductions here, which again I made, but it's easy to fix because your work supports the logic. And so now this is a perfect case of what I've been talking about. I started introducing the multiplicities before I defined it, where now you can look at this and say, oh, cross, cross, cross. You don't have to check all of these symbolically. You could, but like I say, I had students who were thinking, "Oh, Professor Ron, how do I do this symbolically?" I said, "Well, you can actually execute it symbolically by writing nice test points." But then I said, "Let's not work so hard. Let's use the multiplicity." So what I would like you to do when you're studying, and you can come to the conference hours if you want to talk about this some more, is master this problem. If you can do this problem, then you are set to do any problem on the test. So again, just remember, inequalities are only difficult because the computation of the BVs may be complicated. And then we do our work symbolically. Symbolically. That way we do less work and we can easily test. So when I woke up this morning, I thought, oh, I've got a great test question. And then I thought, yeah, let me phrase one of these, do a twofer where I do an easy one and then a more complicated one. But again, as you study for the test, ladies and gentlemen, take all of the review that you've done, like looking at the test, the review test, and you'll see some of the problems I've done have been taken from them. And if you feel very comfortable and you have good feelings, a good foundation, then you are fine. Now for the test, it is okay with me. I know you have your notes. I know you have your book, your all that, your ebook and things like that. It is not a problem for me that you check your notes as you're doing a test. I cannot keep you from doing that. And I have no problem with that because the idea is that if you can construct solutions on the test, it'll be because you know this, you know how to do it. So remember, your work must support the answers you choose. And then within 30 minutes of the timestamp of closing out the Blackboard test, I must have your Turnitin. So I will check the timestamp. Just remember that no work is no credit because you cannot support your work if you don't submit your work. So keep that in mind. I think the test is very fair. I think you will find it to be extremely reasonable. And so again, I will send out email invitations for the conference hours today, and you are welcome to come by, or maybe you're just going to take a nap and say, I'm going to rest up so I can take Professor Ron's test one. So I wish you well. If you come to conference hours, that'll be nice. If you have some questions that you need for me to answer, just send me a WebAssign message and I'll be more than happy to help you out. Well, wintertime is here. Wintertime is here. The cold weather is here. And I looked at the forecast. It's going to be rainy and cold. And I'm thinking, no good. So, I'm going to have to be running in the rain. So I guess I'm going to be even more congested. But enjoy the cool weather if you like it. If not, I guess maybe in a week or so it'll be warm again. So everybody have a great day. And I appreciate your attention today. And again, if other colleagues in the class missed the lecture, I will put this up with the Blackboard link so you can share that with them. So everybody have a great day. You too. Everybody have a great day. You all are very nice and I appreciate it. You make my day. Thank you so much.